Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. Imagine an enterprise billing agent pushes $10,000 in refunds to the wrong accounts over a weekend. Nobody catches it until Monday morning. The model may have worked exactly as designed. The production system around it failed. Maybe the wrong customer context was retrieved. Maybe authorization wasn't enforced. Maybe the tool parameters weren't validated. Maybe a failed request was retried and executed twice. That's the real challenge with agentic AI. Getting a model to call a tool is relatively easy. Making that action safe, reliable, observable, and recoverable in production is much harder. And that's where the career opportunity begins. Industry research shows a major gap between organizations experimenting with AI agents and organizations successfully scaling them. Companies don't just need people who can build agent demos. They need engineers who can close that production gap. So what actually makes an AI system an agent? It's not simply memory. And it's not just calling an API. An agent is typically working toward a goal while making decisions about what actions to take. It receives context about the current situation. It determines what should happen next. It may call a tool, query a system, retrieve information, or ask for clarification. Then it observes the result and decides whether another step is necessary. Think, goal, context and state, decision, action, observation, repeat when necessary. Some agents complete that loop once. Others execute several steps before reaching a stopping condition. The important idea isn't that an agent runs forever. It's that the system can decide what action to take next based on the state of the task. A chatbot and an agent can both use language models, both can have conversational history, and both can potentially call tools. The difference is primarily in how much responsibility the system has for deciding and executing the next step. A traditional chatbot is usually centered around responding to the user's request. An agent can be given a goal and then decide, what information do I need? Which tool should I use? What action should I take? Did that action succeed? Do I need another step? Should I stop? Should I escalate to a human? So don't use memory alone to decide whether something is agentic. Look for goal-directed decision-making, state, actions, and feedback from the environment. That's the more useful distinction. Here's one of the biggest lessons in this video. A production agent is not just an AI model. Think of the model as the decision engine inside a much larger system. Around it, you still need three things. First, integration. The agent has to communicate safely with APIs, databases, business applications, and other tools. Second, control. You need identity, permissions, validation, and policies deciding what the agent is actually allowed to do. And third, operations. You need testing, monitoring, deployment, cost management, and a plan for what happens when something fails. That's why traditional IT and software engineering experience transfers so well into agentic AI. If you already understand cloud systems, APIs, DevOps, security, or backend engineering, you're not starting over. You're learning how to add an AI decision layer to systems you already know how to operate. Here's the market signal behind this video. Organizations are experimenting heavily with AI, but successfully scaling agentic systems remains much less common. That's important because experimentation and production are two very different problems. A proof of concept might only need to demonstrate the agent can call this tool. Production has to answer much harder questions. Who is authorized to call it? What happens if it fails? Can the action be safely retried? How do we evaluate the result? How do we monitor it? How much does it cost? What happens when the model makes the wrong decision? How does a human intervene? That gap between demonstration and dependable operation is where production engineering becomes valuable. Industry experts break enterprise agents into 3 levels. Task agents handle one action: approve an expense, retrieve a record. Workflow agents orchestrate a chain: check inventory, route to warehouse, update the dashboard. Collaborative agents coordinate across departments, say a fraud agent pinging both the transactions API and the compliance team. Knowing which type you're building changes your architecture completely. Agent frameworks are going to change. Models are going to change. Some of the tools everyone talks about today may look completely different a few years from now. So what should you actually learn? Focus on 3 durable skill groups. First, how agents get information. That means context, retrieval, and state. Second, how agents take actions safely. That means tools, permissions, validation, and human approval. Third, how agents survive production. That means evaluation, observability, reliability, and cost control. If you understand those 3 categories, switching from one framework to another becomes much easier. Don't build your career around an agent library. Build it around the production problems every agent platform has to solve. Agentic AI is still early enough that many organizations are working out how to move from prototypes to dependable production systems. That's a useful window for engineers. You don't need to predict the exact year agent adoption reaches some magical inflection point. And you don't need to panic that you're already too late. Instead, focus on what organizations will continue to need as adoption grows. Engineers who understand APIs, cloud infrastructure, data, identity, security, observability, distributed systems, and AI-specific capabilities such as retrieval, evaluation, tool use, and model behavior. Those are durable skills. Learn them now, and you're preparing for the engineering problems companies encounter when their AI experiments become real production systems. Many AI initiatives struggle when they move beyond the prototype stage. That's not necessarily because the model is bad. The problem may be everything surrounding it. Poor data, weak integration, no evaluation strategy, missing security controls, unclear ownership, unreliable tools, no monitoring, uncontrolled cost, or workflows that should never have been autonomous in the first place. That's the career signal. Companies need engineers who can identify those production risks and design systems around them. Don't focus on a dramatic failure percentage. Focus on why scaling is difficult. Those engineering problems are the skills worth learning. Many IT professionals want to learn AI, but formal workplace training isn't always available or fast enough to keep pace with the technology. That means you may have to build part of the skill set yourself. The good news is that you don't need permission to start. You can learn Python, build APIs, experiment with managed AI platforms, create agents that use tools, add retrieval, add evaluation, containerize the application, deploy it, monitor it, and document the architecture. That creates something much more useful than saying, I'm interested in agentic AI. You can show, I built this system, here's how it works, here's how I tested it, and here's how I made it safer. Imagine a developer does extremely well on the AI portion of a technical interview. They understand prompting, few-shot examples, structured outputs, tool calling. Then the interviewer asks, how would you deploy an agent that can issue customer refunds without accidentally refunding the wrong customer or processing the same transaction twice? Now the interview changes. How do you authenticate the user? How do you authorize the action? Where is workflow state stored? How do you validate the refund parameters? Which actions require approval? What happens if the payment API times out? How do you prevent a duplicate transaction? How do you trace what happened afterward? That's the production skill gap. Prompting still matters. But prompting alone doesn't prepare you to engineer a system that can safely take real-world actions. Let's turn production agentic AI into 7 layers. Number 1, context. Give the agent the right information at the right time. Number 2, identity and authorization. Control who can request an action and what the agent is allowed to do on their behalf. Number 3, observability. Make the workflow traceable so you can understand what happened when something fails. Number 4, guardrails and human oversight. High-risk actions should have explicit policies and approval paths. Number 5, evaluation. Test whether your agent actually performs the task correctly before and after every major change. Number 6, cost and performance. Control loops, latency, model usage, and tool usage. And number 7, reliability. Design for retries, failures, interrupted workflows, and safe recovery. You don't need to memorize every implementation detail yet. Remember the 7 layers. That's the difference between building an agent demo and engineering an agent service. Don't start by trying to memorize every agent framework. Start with the capabilities you need. You need model access. You need tool integration. You may need workflow and state orchestration. You need retrieval and context management. You need evaluation, and you need observability. Frameworks such as LangChain, LangGraph, Crew AI, and other agent development tools can help implement parts of that architecture. Observability and evaluation platforms can help you trace and test what the system is doing. But treat those products as examples. The framework landscape changes quickly. The durable skill is understanding what each layer is responsible for and being able to replace one implementation without redesigning your entire mental model. Learn the architecture first. Then learn the tools that help you implement it. Let's break a simple agent into its components. First, the agent receives a goal. For example, find the urgent support tickets assigned to my team. The system provides the model with the relevant instructions and current state. The model determines that it needs ticket data. Instead of inventing an answer, it selects an approved ticket retrieval tool. Your application validates the tool request. The tool queries the ticket system. The result returns to the agent. The agent evaluates that result and decides whether it has enough information to answer. If it does, it responds. If it doesn't, it may take another permitted step. That's the anatomy: goal, context, state, decision, tool, observation, stopping condition. The real engineering challenge is making every one of those transitions secure, observable, testable, and recoverable. Context engineering sounds complicated, so think of it this way. Imagine you're sending a technician to repair a server. You wouldn't hand them your entire company's documentation archive. You'd give them the information they need for that specific job: the ticket, the affected system, the relevant runbook, their permissions, and the tools they're allowed to use. That's context engineering. For an AI agent, you want to assemble the same kind of focused workbench. Give it the relevant knowledge. Retrieve additional information when needed. Preserve the state of the current task. Apply the policies that matter. And make the available tools clear. Too little context and the agent guesses. Too much context and important information gets buried in noise. Good context engineering is about giving the agent the right information, not all the information. Agentic patterns can be applied across many industries and business functions. In software companies, agents can assist with support, development workflows, and internal operations. Financial organizations can use agentic workflows to assist fraud investigation, document review, or customer service processes. Healthcare organizations may explore them for administrative workflows such as intake and document processing, with appropriate privacy and human oversight. Cybersecurity teams can use agents to enrich alerts, gather evidence, and assist response workflows. Logistics and e-commerce teams can use them to coordinate information across inventory, orders, shipping, and customer service. And large enterprises can use agents internally to connect knowledge, applications, APIs, and business processes. The opportunity isn't tied to one industry. The common problem is integration. How do you safely connect AI decision-making to real enterprise systems? This may be the most important security rule in the video. The model should never be your security boundary. Suppose an agent decides, I should issue a $5,000 refund. That doesn't mean the refund should happen. Your application still needs to authenticate the user, authorize the action, Validate the customer and transaction. Enforce refund limits. Protect sensitive data. Apply business policies. Require approval when the risk is high. And record the final action for audit. The agent can propose an action. Your trusted application layer decides whether that action is permitted. That distinction matters. LLMs are probabilistic systems. Authentication, authorization, transaction limits, and security policies should be enforced by deterministic controls outside the model. Production agents need observability because a single user request may trigger multiple model calls, retrieval steps, and tool actions. Start with structured telemetry. Track the request or workflow ID. Record state transitions. Trace which tool was selected. Capture safe, appropriate tool parameters and results. Measure model and tool latency. Track token usage and cost. Record errors, retries, and timeouts. And attach evaluation results when you're measuring response or workflow quality. The goal isn't to capture hidden internal reasoning. The goal is to capture enough operational evidence to answer what happened, which component made the decision, which tool was called, did it succeed, how long did it take, how much did it cost, and where did the workflow fail? That's what lets you debug an agent like a production system. So what does an agentic AI engineer actually spend time doing? A significant part of the job is still software engineering. Writing application code, designing APIs, managing state, integrating tools, and deciding how components communicate. Another major part is testing and debugging. Why did the agent choose the wrong tool? Why did retrieval return bad context? Why did a workflow get stuck? Why did latency increase? You'll also work on observability, security, evaluation, deployment, data quality, and cost management. And yes, you'll work with product teams and business stakeholders because somebody has to define what the agent should and should not be allowed to do. The exact mix varies by organization, but one thing is consistent. Production agent engineering is much broader than prompt writing. If you already have backend, DevOps, cloud, platform, SRE, security, or systems experience, that background can transfer extremely well into agentic AI. Why? Because you've already encountered production problems. APIs fail, networks time out, dependencies go down, credentials expire, deployments break, traffic spikes, logs fill up, and users do things you never expected. Agentic systems don't make those problems disappear. They add another probabilistic component on top of them. So don't think, I have to throw away my IT experience and become an AI researcher. Think, how do I add models, retrieval, tools, evaluation, and agent orchestration to the production engineering skills I already have? That's a much stronger career bridge. You don't have to learn agentic AI all at once. Build it in layers. Start with software fundamentals, Python, APIs, Git, testing. Then build one small agent with one or two tools. Once that works, add state and retrieval so the agent can maintain context and access external knowledge. Next, add the controls that make the system safer, authorization, evaluation, and human approval for sensitive actions. Then deploy it. Add monitoring, cost tracking, and failure testing. Finally, harden it with reliability patterns such as retries, durable state, and idempotency. Notice what's not at the end of this roadmap. Build 10 agents. Multi-agent systems are optional. Production reliability is not. Here's the same learning path as one simple visual. Foundation, Python, APIs, Git, testing. Then, tool use. Give the agent one safe way to interact with another system. Then, context. Add state and retrieval. Then, control. Add authorization, evaluation, and guardrails. Then, production. Deploy it with monitoring, cost controls, and observability. And finally, reliability. Test retries, failures, interrupted workflows, and recovery. That's the roadmap. You don't graduate because your architecture has the most agents. You graduate when the system can perform useful work reliably. Let's walk through a small support triage agent. The user asks, "Show me the urgent tickets assigned to my team." The agent first determines that it needs live ticket data. It selects the approved ticket retrieval tool and sends a structured request. The tool returns the matching tickets. The agent then uses that result to produce a ranked summary for the user. Now comes the part that matters in production. Open the trace. You should be able to see the workflow state, which tool was selected, whether the call succeeded, how long it took, and what information was returned. If the result is wrong, you now have something concrete to investigate. Was the wrong tool selected? Were the arguments incorrect? Did the API return unexpected data? Was important context missing? That trace turns agent debugging from guesswork into engineering. The goal of this demo isn't simply to prove that the agent can call a tool. It's to show that you can understand and troubleshoot the complete workflow. Here's a useful mental model for understanding an agent loop. First, context. What does the system know about the goal, user, policies, and current state? Second, plan. Given that context, what should happen next? Third, act. Call an approved tool, retrieve information, ask for clarification, or perform another permitted operation. Fourth, evaluate. What happened? Did the action succeed? Did we get the information we needed? Should we continue, stop, retry, or escalate? Then the updated state becomes context for the next step. Think, context, plan, act, evaluate. It's not the only way to design an agent. It's a practical model for understanding how goal-directed systems can take multiple, controlled steps. Here's something every production agent needs: a stopping condition. After an action completes, the system evaluates the result. Maybe the goal is complete. Stop. Maybe more information is required. Continue. Maybe the tool failed. Retry according to policy or choose another permitted path. Maybe the risk becomes too high. Escalate to a human. And maybe the agent has already used the maximum number of permitted steps. Stop. That's important because an autonomous loop without limits can create reliability, latency, and cost problems. So when you design an agent, don't only ask, how does it decide the next action? Also ask, under what conditions must it stop? Here are 5 mistakes worth remembering. First, bad context. If the agent gets stale, incomplete, or irrelevant information, everything downstream becomes harder. Second, no evaluation. If you don't test behavior, you won't know whether your latest change actually improved anything. Third, uncontrolled cost and latency. Agent loops can multiply model and tool calls quickly. Fourth, too many tools. Give the agent only the capabilities it actually needs. And fifth, trusting the model to enforce your rules. Authorization, parameter validation, transaction limits, and high-risk approvals belong outside the model. Think of these 5 as your production warning signs: bad context, no tests, no limits, too many tools, and too much trust in the model. When you're estimating agent cost, don't stare at token prices in isolation. Think about the entire task. Imagine one support request. The agent calls the model, then searches the knowledge base, then calls a ticket API, then calls the model again to evaluate the result. One user request has already become several billable operations. And if the workflow retries, the cost grows again. So measure. How many steps does a successful task require? How often does the agent retry? And what does one completed task actually cost? Then control it. Limit the number of steps. Use timeouts. Reduce unnecessary context. Cache reusable information when appropriate. And use less expensive models where they still meet your quality requirements. The metric that matters isn't simply cost per model call. It's cost per useful outcome. Let's return to our refund agent. The agent calls the payment API, refund $500. The payment system successfully processes the refund. But before the success response reaches your agent, the network times out. From the agent's perspective, the action may look like it failed. So it retries. Now you've refunded $1,000. That's why production agent engineering needs more than good prompts. For actions that change real systems, design for idempotency so retries don't accidentally execute the same transaction twice. Use timeouts and retry policies. Persist durable workflow state. Track transaction identifiers. Use circuit breakers when dependencies are unhealthy. And design compensation or recovery workflows for partial failures. This is where traditional distributed systems engineering becomes extremely valuable. The agent decides what it wants to do. Your production architecture makes sure that action happens safely, exactly as intended. Consider a traditional IT support workflow. A ticket arrives. A technician reads it, determines the category, searches for relevant documentation, and decides whether the issue can be resolved or needs escalation. AI can assist with several of those steps. An agent might classify the ticket, retrieve relevant knowledge base articles, gather approved contextual information from other systems, and recommend the next action. But the human doesn't disappear. Low-risk, well-understood tasks may be handled automatically when the system has appropriate controls. Ambiguous, sensitive, or high-impact requests can be routed to a technician for review. That's the useful shift. The support team spends less time on repetitive triage and more time on exceptions, judgment, and complex troubleshooting. The goal isn't autonomous IT for its own sake. It's using AI to improve how human operators manage the workflow. If you want one portfolio project from this video, build an IT support triage agent. Keep the first version small. It receives a ticket, it classifies the issue, it searches the knowledge base, and it recommends what should happen next. Then add the production layers one at a time. First, authentication and permissions. Second, logging and traceability. Third, evaluation. Fourth, human approval for sensitive actions. And fifth, failure testing. What happens when retrieval finds nothing? What happens when the ticket API is unavailable? What happens when the model asks for an action it isn't allowed to perform? Now you have a project you can actually discuss in an interview, not, I built a chatbot. But, I built an agent, secured its tools, evaluated its behavior, monitored its workflow, and tested how it fails. That's a much stronger engineering story. Quick checkpoint. What was the central market problem we started with? Organizations are experimenting with AI agents much faster than they're successfully scaling them into dependable production systems. That's the gap. And now you know why it exists. Production requires more than a model and a prompt. It requires context, tools, state, authorization, evaluation, observability, guardrails, cost controls, failure recovery, and disciplined deployment. That's the skill stack this entire lesson is designed around. Here's your challenge for this week. Don't build another weather agent. Build a small IT agent. Give it one job. Triage a support ticket. Start with one or two tools. For example, a knowledge-based search tool and a ticket lookup tool. Give the agent a clear goal. Let it retrieve relevant information. Let it recommend a next action. Then add one important safety rule. The agent can recommend a change, but it cannot execute a high-risk action without approval. Once that works, add logging. Then evaluation. Then error handling. Then deploy it. You don't need 10 agents. You don't need 20 tools. You need one small agent whose architecture you can explain from end to end. Build that, document it, and you've started creating evidence that you understand production agent engineering. You've seen the architecture behind a production agent. Now it's time to build one. In the next hands-on lesson, we'll use LangChain as the implementation tool. But the goal isn't to memorize LangChain. We'll use it to practice the durable concepts from this video: tool calling, state, context, guardrails, and observability. If another framework replaces it later, those engineering principles still transfer. Watch the hands-on agent tutorial next. Build alongside me and focus on understanding why each piece exists, not just which library function we call. That's how you turn a framework tutorial into an engineering skill. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.